Namaste. Myself Ankita Shreya Prasad, and you are listening to along with our NCERT 11th and 12th audio video book presented by ART.SKILL.PASSION. Chapter 14: Semiconductor Electronics, Materials, Devices and Simple Circuits. 14.1 Introduction. Devices in which a controlled flow of electrons can be obtained are the basic building blocks of all the electronic circuits. Before the discovery of transistors in 1948, such devices were mostly vacuum tubes, also called valves, like the vacuum diode, which has two electrodes, that is, anode, often called plate, and cathode, triode, which has three electrodes, cathode plate and grid, tetrode and pentode respectively, with 4 and 5 electrodes. In a vacuum tube, the electrons are supplied by a heated cathode, and the controlled flow of these electronics in vacuum is obtained by varying the voltage between its different electrodes. Vacuum is required in the inter-electrode space. Otherwise, the moving electrons may lose their energy on collision with the air molecules in their path. In these devices, the electrons can flow only from the cathode to the anode, that is, only in one direction. Therefore, such devices are generally referred to as valves. These vacuum tube devices are bulky, consume high power, operate generally at high voltage, equivalent to 100 volts, and have limited life and low reliability. The seed of the development of modern solid-state semiconductor electronics goes back to 1930s, when it was released that some solid-state semiconductor and their junctions offer the possibility of controlling the number and the direction of flow of charge carriers through them. Simple excitations like light, heat or small applied voltage can change the number of mobile charges in a semiconductor. Note that the supply and flow of charge carriers in the semiconductor devices are within the solid itself. While in the earlier vacuum tubes valves, the mobile electrons were obtained from a heated cathode and they were made to flow in an evacuated space or vacuum. No external heating or large evacuated space is required by the semiconductor devices. They are small in size, consume low power, operate at low voltage, and have long life and high reliability. Even the cathode ray tube (CRT) used in television and computer monitors, which work on the principle of vacuum tubes, are being replaced by liquid crystal display (LCD) monitors with supporting solid-state electronics. Much before the full implication of the semiconductor devices were formally understood, a naturally occurring crystal of galena lead sulfide (PBS) with a metal point contact attached to it was used as detector of radio waves. In the following session, we will introduce the basic concepts of semiconductor physics and discuss some semiconductor devices like junction diodes, a two-electrode devices, and bipolar junction transistor, a three-electrode device. A few circuits illustrating their applications will also be described. 14.2 Classification of metals, conductors and semiconductors. On the basis of conductivity, on the basis of the relative values of electrical conductivity, sigma, or resistivity, rho is equal to 1 by sigma. The solids are broadly classified as first metals. They possess very low resistivity or high conductivity. Rho equivalents to 10 to the power minus 2 to 10 to the power minus 8 ohm. Sigma is equivalent to 10 to the power 2 2 10 to the power 8 s meter to the inverse. Second, semiconductors, they have resistivity or conductivity in the intermediate to metals and insulators. Rho equivalents to 10 to the power minus 5 to 10 to the power 6 ohm hem. Sigma 10 to the power 5 to 10 to the power minus 6 s to the power of minus 1. Third, insulators, they have high resistivity or low conductivity. Rho equivalents to 10 to the power 11 to 10 to the power 19 rho m. Sigma 10 to the power minus 11 to 10 to the power minus 19 s meter inverse. The values of rho and sigma given above are indicative of magnitude and could well go outside the ranges as well. Relative values of the resistivity are not the only criteria for distinguishing metals, insulators and semiconductors from each other. There are some other differences which will become clear as we go along in this chapter. Our interest in this chapter is in the study of semiconductors, which could be first, elemental semiconductors Si and Ge. Second, compound semiconductors. Examples are inorganic CdS, GaAs, CdSe, InP, etc. Inorganic, anthracene doped phthalocanins, etc. Organic polymers, polypyrrole, polyaniline, polythiophene, etc. Most of the currently available semiconductor devices are based on elemental semiconductors Si or Ge and compound inorganic semiconductors. However, after 1990, a few semiconductor devices using organic semiconductors and semiconducting polymers have been developing, signaling the birth of futuristic technology of polymer electronics and molecular electronics. In this chapter, we will restrict ourselves to the study of inorganic semiconductors, particularly elemental semiconductors Si and Ge. The general concepts introduced here for discussing the elemental semiconductors by and large apply to most of the compound semiconductors as well. On the basis of energy bands according to the Bohr atomic model, in an isolated atom, the energy of any of its electrons is decided by the orbit in which it revolves. But when the atoms come together to form a solid, they are closely to each other. So the outer orbit of electrons from neighboring atoms would come very close or could even overlap. This would make the nature of electron motion in a solid very different from that in an isolated atom. Inside the crystal, each electron has a unique position and no two electrons sees exactly the same pattern of surrounding charges. Because of this, each electron will have a different energy level. These different energy level with continuous energy variation from what are called energy bands. The energy band, which includes the energy level of the valence electrons, is called the valence band. The energy band above the valence band is called the conduction band. With no external energy, all the valence electrons will reside the valence band. If the lowest level in the conduction band happens to be lower than the highest level of the valence band, the electrons from the valence band can easily move into the conduction band. Normally, the conduction band is empty, but when it overlaps on the valence band, electrons can move freely into it. This is the case with metallic conductors. If there is some gap between the conduction band and the valence band, electrons in the valence band are remain bound and no free electrons are available in the conduction band. This makes the material an insulator. But some of the electrons from the valence band may gain external energy to cross the gap between the conduction band and the valence band. Then these electrons will move into the conduction band. At the same time, they will create vacant energy levels in the valence band where other valence electrons can move. Thus, the process creates the possibility of conduction due to electrons in conduction band as well as due to valencies in the valence band. Let us consider what happens in the case of Si or Ge crystal containing n atoms. For Si, the outermost orbit is the third orbit, n is equal to 3, while for Ge it is the fourth orbit, n is equal to 4. The number of electrons in the outermost orbit is 4, 2s and 2p electrons. Hence, the total number of outer electrons in the crystal is 4n. The maximum possible number of electrons in the outer orbit is 8, 2s plus 6p electrons. So, for the 4n valence electrons, there are 8n available energy states. These 8n discrete energy levels can either form a continuous band or they may be grouped in different bands depending upon the distance between the atoms in the crystal. See box on band theory of solids. At the distance between the atoms in the crystal lattice of Si and Ge, the energy band of these 8n states is split apart into two, which are separated by an energy gap, e.g. Figure 14.1. The lower band, which is completely occupied by the 4n valence electrons at temperature of absolute zero, is the valence band. The other band, consisting of 4n energy states called the conduction band, is completely empty at absolute zero. The lowest energy level in the conduction band is shown as Ec and the highest energy level in the valence band is shown as Ev. Above Ec and below Ev, there are large number of closely spaced energy levels as shown in figure 14.1. The gap between the top of the valence band and bottom of the conduction band is called the energy band gap. Energy gap, e.g., it may be large, small or zero depending upon the material. These different situations are depicted in figure 14.2 and discussed below. Case 1. This refers to a situation as shown in figure 14.2a. One can have a metal either when the conduction band is partially filled and the valence band is partially empty, or when the conduction and valence band overlap. When there is overlap, electrons from valence band can easily move into the conduction band. This situation makes a large number of electrons available for electrical conduction when the valence band is partially empty. Electrons from its lower level can move to higher level, making conduction possible. Therefore, the resistance of such materials is low or the conductivity is high. Case 2. In this case, as shown in figure 14.2b, a large band gap Eg exists. Eg is greater than 3 eV. There are no electrons in the conduction band and therefore no electrical conduction is possible. Note that the energy gap is so large that electrons cannot be excited from the valence band to the conduction band by thermal excitation. This is the case of insulators. Case 3. This situation is shown in figure 14.2c. Here a finite but small band gap Eg is smaller than 3 eV exists. Because of the small band gap at room temperature, some electrons from valence band can acquire enough energy to cross the energy gap and enter the conduction band. These electrons, though small in numbers, can move in the conduction band. Hence, the resistance of semiconductors is not as high as that of the insulators. In this section, we have made a broad classification of metals, conductors and semiconductors. In this session which follows, you will learn the conduction processes in semiconductors. 14.3. Intrinsic Semiconductors. We shall take the most common case of Ge and Si, whose lattice structure is shown in figure 14.3. These structures are called the diamond-like structure. Each atom is surrounded by 4 nearest neighbors. We know that Si and Ge have 4 valence electrons in its crystalline structure. Every Si or Ge atom tends to share one of its 4 valence electrons with each of its 4 nearest neighbor atoms, and also to take share of 1 electron from each such neighbor. These shared electron pairs are referred to as forming a covalent bond or simply a valence bond. The 2 shared electrons can be assumed to shuttle back and forth between the associated atoms, holding them together strongly. Figure 14.4 schematically shows the 2-dimensional representation of Si or Ge structure shown in figure 14.3, which overemphasizes the covalent bond. It shows an idealized picture in which no bonds are broken. All bonds are intact. Such a situation arises at low temperatures. As the temperature increases, more thermal energy becomes available to these electrons, and some of these electrons may break away, becoming free electrons, contributing to conduction. The thermal energy effectively ionizes only few atoms in the crystalline lattice and creates a vacancy in the bond as shown in figure 14.5a. The neighborhood from which the free electron with charges Q has come out levels a vacancy with an effective charge plus Q. This vacancy with the effective positive electronic charge is called a hole. The hole behaves as an apparent free particle with effective positive charge. In intrinsic semiconductor, the number of free electrons Ne is equal to the number of holes NH, that is Ne is equal to NH is equal to Ni, where Ni is called the intrinsic carrier concentration. Semiconductor possesses the unique property in which apart from electrons the holes also move. Suppose there is a hole at site 1 as shown in figure 14.5a. The movement of holes can be visualized as shown in figure 14.5b. An electron from the covalent bond at site 2 may jump to the vacant site 1 hole. Thus, after such a jump, the hole is at site 2 and the site 1 has now an electron. Therefore, apparently the hole has moved from site 1 to site 2. Note that the electron originally set free. Figure 14.5a is not involved in this process of hole motion. The free electron moves completely independently as conduction electron and gives rise to an electron current, i.e. under an applied electric field. Remember that the motion of hole is only a convenient way of describing the actual motion of bound electrons. Whenever there is an empty bond anywhere in the crystal, under the action of an electric field, these holes move towards negative potential, giving the hole current IH. The total current IE is thus the sum of the electron current IE and the hole current IH. I is equal to IE plus IH. It may noted that apart from the processes of generation of conduction electrons and holes, a simultaneous process of recombination occurs in which the electrons recombine with the holes. At equilibrium, the rate of generation is equal to the rate of recombination of charge carriers. The recombination occurs due to an electron colliding with a hole. An intrinsic semiconductor will behave like an insulator at T is equal to 0 Kelvin as shown in figure 14.6a. It is the thermal energy at the higher temperature. T is greater than OK, which excites some electrons from the valence band to the conduction band. These thermally excited electrons at T is larger than 0 Kelvin partially occupy the conduction band. Therefore, the energy band diagram of an intrinsic semiconductor will be as shown in figure 14.6b. Here some electrons are shown in the conduction band. These have come from the valence band, leaving equal numbers of holes there. 14.4 Extrinsic Semiconductor. The conductivity of an intrinsic semiconductor depends on its temperature, but at room temperature its conductivity is very low. As such, no important electronic devices can be developed using these semiconductors. Hence, there is a necessity of improving their conductivity. This can be done by making use of impurities. When a small amount, say a few parts per million ppm of a suitable impurity is added to the pure semiconductor, the conductivity of the semiconductor is increased manifold. Such materials are known as extrinsic semiconductors or impurity semiconductors. The deliberate addition of a desirable impurity is called doping, and the impurity atoms are called dopants. Such a material is also called a doped semiconductor. The dopant has to be such that it does not distort the original pure semiconductor lattice. It occupies only a very few of the original semiconductor atom sites in the crystal. A necessary condition to attain this is that the size of the dopant and the semiconductor atoms should be nearly the same. There are two types of dopants used in doping: the trivalent Si or Ge, first pentavalent valency file like arsenic As, antimony Sb, phosphorus P, etc. Second, trivalent valency 3 like indium In, boron B, aluminium Al, etc. We shall now discuss how the doping changes the number of charge carriers and hence the conductivity of semiconductors. Si or Ge belongs to the fourth group in the periodic table, and therefore we choose the dopant element from nearby fifth or third group, expecting and taking care that the size of the dopant atom is nearly the same as that of Si or Ge. Interestingly, the pentavalent and trivalent dopant in Si or Ge give two entirely different types of semiconductors as discussed below. First, N-type semiconductor. Suppose we dope Si or Ge with pentavalent element as shown in figure 14.7. When an atom of +5 valency element occupies the position of an atom in the crystal lattice of Si, 4 of its electron bond with the 4 silicon members, while the 5th remains very weakly bound to its parent atom. This is because the 4 electrons participating in the bonding are seen as part of the effective core of the atom by the 5th electron. As a result, the ionization energy required to set this electron free is very small, and even at room temperature it will be free to move in a lattice of semiconductor. For example, the energy required is 0.01 eV for germanium and 0.05 eV for silicon. To separate this electron from its atom, this is in contrast to the energy required to jump the forbidden band, about 0.72 eV for germanium and about 1.1 eV for silicon at room temperature in the intrinsic semiconductor. Thus, the pentavalent dopant is donating one extra electron for conduction and hence is known as donor impurity. The number of electrons made available for conduction by dopant atoms depends strongly upon the doping level and is independent of an increase in ambient temperature. On the other hand, the number of free electrons with an equal number of holes generated by Si atom increases weakly with temperature. In a doped semiconductor, the total number of conduction electrons Ne is due to the electrons contributed by donors and those generated intrinsically, while the total number of holes NH is only due to the holes from the intrinsic source, but the rate of recombination of holes would increase due to the increase in the number of electrons. As a result, the number of holes would get reduced further. Thus, with proper level of doping, the number of conduction electrons can be made much larger than the number of holes. Hence, in an extrinsic semiconductor doped with pentavalent impurity, electrons become the majority carrier and holes the majority carriers. These semiconductors are therefore known as N-type semiconductors. For N-type semiconductors, we have Ne is lot more greater than NH. Second, P-type semiconductors. This is obtained when Si or Ge is doped with a trivalent impurity like Al, B, In, etc. The dopant has one valence electron less than Si or Ge and therefore this atom can form covalent bond with neighboring 3 Si atoms but does not have any electron to offer to the fourth Si atom. So the bond between the fourth neighbor and the trivalent atom has a valency or holes as shown in figure 14.8. Since the neighboring Si atom in the lattice valent an electron in a place of a hole, an electron in the outer orbit of an atom in the neighboring hood may jump to fill this vacancy, leaving a vacancy or hole at its own site. Thus, the hole is available for conduction. Note that the trivalent foreign atom becomes effectively negatively charged when it shares fourth electron with neighboring Si atom. Therefore, the dopant atom of P-type material can be treated as core of one negative charge along with its associated hole as shown in figure 14.8b. It is obvious that one acceptor atom gives one hole. These holes are in addition to the intrinsically generated holes, while the source of conduction electrons is only intrinsic generation. Thus, for such material, the holes are the majority carriers and electrons are minority carriers. Therefore, extrinsic semiconductors doped with trivalent impurities are called P-type semiconductors. For P-type semiconductors, the recombination processes will reduce the number Ni of intrinsically generated electrons to Ne. We have for P-type semiconductors, NH is greater than Ne. Note that the crystal maintains an overall charge neutrality as the charge of addition charge carriers is just equal and opposite to that of the ionized cores in the lattice. In extrinsic semiconductors, because of the abundance of the majority current carriers, the minority carriers produced thermally have more chance of melting majority carriers and thus getting destroyed. Hence, the dopant, by adding a large number of current carriers of one type, which become the majority carriers indirectly, helps to reduce the intrinsic concentration of minority carriers. The semiconductor energy band structure is affected by doping. In the case of extrinsic semiconductors, additional energy states due to donor impurities ED and acceptor impurities EA also exist. In the energy band diagram of N-type Si semiconductor, the donor energy level ED is slightly below the bottom EC of the conduction band, and electrons from this level move into the conduction band with very small supply of energy at room temperature. Most of the donor atoms get ionized, but very few 10 to the power 12 atoms of Si get ionized. So the conduction band will have most electrons coming from the donor impurities as shown in figure 14.9a. Similarly, for p-type semiconductor, the acceptor energy level EA is slightly above the top EV of the valence band as shown in figure 14.9b. With very small supply of energy, an electron from the valence band can jump to the level EA and ionize the acceptor negatively. Alternatively, we can also say that with very small supply of energy, the hole from level EA sinks down into the valence band. Electrons rise up and holes falls down when they gain external energy. At room temperature, most of the acceptor atoms get ionized, leaving holes in the valence band. Thus, at room temperature, the density of holes in the valence band is predominantly due to impurity in the extrinsic semiconductor. The electron and hole concentration in a semiconductor in thermal equilibrium is given by NE/NH is equal to Ni square. Through the above description is grossly approximate and hypothetical. It helps in understanding the difference between metals, insulators and semiconductors, extrinsic and intrinsic, in a simple manner. The difference in the resistivity of C, Si and Ge depends upon the energy gap between their conduction and valence band. For C diamond, Si and Ge, their energy gaps are 5.4 eV, 1.1 eV and 0.7 eV respectively. Sn also is a group 4 element, but it is a metal because the energy gap in its case is 0 eV. 14.5 Pn junction. A Pn junction is the basic building blocks of many semiconductor devices like diodes, transistors, etc. A clear understanding of the junction behavior is important to analyze the working of other semiconductor devices. We will now try to understand how a junction is formed and how the function behaves under the influence of external applied voltage, also called bias. 14.5.1 Pn Junction Formation. Consider a thin p-type silicon PSI semiconductor wafer by adding preciously a small quantity of pentavalent impurity. Part of the PSI wafer can be converted into NSI. There are several processes by which a semiconductor can be formed. The wafer now contains P region and N region and a metallurgical junction between P and N region. Two important processes occur during the formation of a P and N junction: diffusion and drift. We know that in an N-type semiconductor, the concentration of electrons, number of electrons per unit volume, is more compared to the concentration of holes. Similarly, in a P-type semiconductor, the concentration of holes is more than the concentration of electrons. During the formation of P and N junction, and due to the concentration gradient across P and N sides, holes diffuse from P side to N side, P and N, and electrons diffuse from N side to P side, N to P. This motion of charge carriers gives rise to diffusion current across the junction. When an electron diffuses from N to P, it leaves behind an ionized donor on N side. This ionized donor positive charge is immobile as it is bonded to the surrounding atoms. As the electrons continue to diffuse from N to P, a layer of positive charge or positive space charge region
on inside of the junction is developed. Similarly, when a hole diffuses from P to N due to the concentration gradient, it leaves behind an ionized acceptor negative charge which is immobile. As the holes continue to diffuse, a layer of negative charge or negative space charge region on the P side of the junction is developed. This space charge region on either side of the junction together is known as depletion region, as the electrons and holes taking part in the initial movement across the junction depleted the region of its free charges. The thickness of depletion region is of the order of 1/10 of a micrometer. Due to the positive space charge region on N side of the junction and negative space charge region on P side of the junction, an electric field directed from positive charge towards negative charge develops. Due to this field, an electron on P side of the junction moves to N side and a whole N side of the junction moves to P side. The motion of charge carriers due to the electric field is called drift. Thus, a drift current which is opposite in direction to the diffusion current. Initially, diffusion current is large and drift current is small. As the diffusion process continues, the space charge regions on either side of the junction extend, thus increasing the electric field strength and hence drift current. This process continues until the diffusion current equals the drift current. Thus, a Pn junction is formed. In a Pn junction under equilibrium, there is no net current. The loss of electrons from the N region and the gain of electron by the P region causes a difference of potential across the junction of the two regions. The polarity of this potential is such as to oppose further flow of carriers so that a condition of equilibrium exists. Figure 14.11 show that the P and N junction at equilibrium and the potential across the junction. The N material has lot electrons and P materials has acquired electrons. The N material is thus positive relative to the P material, since this potential tends to prevent the movement of electrons from the N region into the P region. It is often called a barrier potential. 14.6 Semiconductor diode. A semiconductor diode, figure 14.12a, is basically a P and N junction with metallic contacts provided at the ends of the application of an external voltage. It is a two-terminal device. A Pn junction diode is symbolically represented as shown in figure 14.12b. The direction of arrow indicates the conventional direction of current when the diode is under forward bias. The equilibrium barrier potential can be altered by applying an external voltage V across the diode. The situation of Pn junction diode under equilibrium without bias is shown in figure 14.11a and b. 14.6.1 Pn junction diode under forward bias. When an external voltage V is applied across a semiconductor diode such that P side is connected to the positive terminal of the battery and N side to the negative terminal, figure 14.3a, it is said to be forward biased. The applied voltage mostly drops across the depletion region and the voltage drop across the P side and N side of the junction is negligible. This is because the resistance of the depletion region, a region where there are no charges, is very high compared to the resistance of N side and P side. The direction of the applied voltage V is opposite to the built-in potential V0. As a result, the depletion layer width decreases and the barrier height is reduced. Figure 14.3. The effective barrier height under forward bias is V0 minus V. If the applied voltage is small, the barrier potential will be reduced only slightly below the equilibrium value, and only a small number of carriers in the material, those that happen to be in the uppermost energy levels, will possess enough energy to cross the junction, so the current will be small. If we increase the applied voltage significantly, the barrier height will be reduced and more number of carriers will have the required energy. Thus the current increases. Due to the applied voltage, electrons from N side cross the depletion region and reach P side, where there are minority carriers. Similarly, holes from P side cross junction and reach the N side, where there are minority carriers. This process under forward bias is known as minority carrier injection. At the junction boundary on each side, the minority carrier concentration increases significantly compared to the locations far from the junction. Due to this concentration gradient, the injected electrons on P side diffuses from the junction edge of P side to the other end of P side. Likewise, the injected holes on N side diffuse from the junction edge of N side to the other end of N side. Figure 14.4. This motion of charge carriers on either side give rise to current. The total diode forward current is sum of hole diffusion current and convection current due to electron fusion. The magnitude of this current is usually in mA. 14.6.2 Pn Junction Diode under reverse bias. When an external voltage V is applied across the diode such that N side is positive and P side is negative, it is said to be reverse bias. The applied voltage mostly drops across the depletion region. The direction of applied voltage is same as the direction of barrier potential. As a result, the barrier height increases and the depletion region widens due to the change in the electric field. The effective barrier height under reverse bias is V0 plus V. Figure 14.5b. This suppresses the flow of electrons from N to P and holes from P to N. This diffusion current decreases enormously compared to the diode under forward bias. The electric field direction of the junction is such that if electrons on P side or holes on N side in their random motion come close to the junction, they will be swept to its majority zone. This drift of carriers gives rise to current. The drift current is of the order of a few μA. This is quite low because it is due to the motion of carriers from their minority side to their majority side across the junction. The drift current is also there under forward bias, but it is negligible μA when compared with current due to injected carriers, which is usually in mA. The diode reverse current is not very much dependent on the applied voltage. Even a small voltage is sufficient to sweep the minority carriers from one side to the junction to the other side of the junction. The current is not limited by the magnitude of the applied voltage, but is limited due to the concentration of the minority carriers on either side of the junction. The current under reverse bias is essentially voltage independent upon a critical reverse bias voltage known as breakdown voltage VBR. When V is equal to VBR, the diode reverse current increases sharply. Even a slight increase in the bias voltage causes large change in the current. If the reverse current is not limited by an external circuit below the rated value specified by the manufacturer, the Pn junction will get destroyed. Once it exceeds that related value, the diode gets destroyed due to overheating. This can happen even for the diode under forward bias. If the forward current exceeds the rated value, the circuit arrangement for studying the VI characteristics of diode, that is the variation of current as a function of applied voltage, as shown in figure 14.16a and b. The battery is connected to the diode through a potentiometer or rheostat so that the applied voltage to the diode can be changed. For different values of voltage, the value of current is noticed. A graph between V and I is obtained as in figure 14.16. Note that in forward bias measurement we use millimeters since the expected current is large, as explained in the earlier session, while a micrometer is used in reverse bias to measure the current. You can see in figure 14.16 that in forward bias the current first increases very slowly, almost negligibly, till the voltage across the diode crosses a certain value. After the characteristics voltage, the diode current increases significantly, exponentially, even for a very small increase in the diode bias voltage. This voltage is called the threshold voltage or cut-in voltage, equivalent to 0.2 volts for germanium diode and 0.7 volts for silicon diode. For the diode in the reverse bias, the current is very small, nu A, and almost remains constant with change in bias. It is called reverse saturation current. However, for special cases at very high reverse bias breakdown voltage, the current suddenly increases. The special action of the diode is discussed later in section 14.8. The general purpose diode are not used beyond the reverse saturation current region. The above discussion showed that the Pn junction diode primarily allows the flow of current only in one direction forward bias. The forward bias resistance is low as compared to the reverse bias resistance. This property is used for rectification of AC voltage as discussed in the next session. For diodes, we define a quantity called dynamic resistance as the ratio of small change in voltage delta V to a small change in current delta I. RD is equal to delta V by delta I. 14.7 Application of junction diode as a rectifier. From the VI characteristics of a junction diode, we see that it allows current to pass only when it is forward bias. So, if an alternating voltage is applied across a diode, the current flows only in that part of the cycle when the diode is forward bias. This property is used to rectify alternating voltage, and the circuit used for this purposes is called a rectifier. If an alternating voltage is applied across a diode in a series with a load, a pulsating voltage will appear across the load only during the off cycles of the AC input, during which the diode is forward bias. Such rectifier circuit as shown in figure 14.18 is called a half-wave rectifier. The secondary of a transformer supplies the desired AC voltage across terminals A, B and B. When the voltage at A is positive, the diode is forward biased and is conducts when A is negative. The diode is reverse biased and it does not conduct. The reverse saturation current of a diode is negligible and can be considered equal to 0 for practical purposes. The reverse breakdown voltage of the diode must be sufficiently higher than the peak AC voltage at the secondary of the transformer to protect the diode from reverse breakdown. Therefore, in the positive half cycle of AC, there is a current through the load resistor RL, and we get an output voltage as shown in figure 14.18b. Whereas there is no current in the negative half cycle. In the next positive half cycle, again we get the output voltage. Thus, the output voltage through still varying is restricted to only one direction and is said to be rectified. Since the rectified output of this circuit is only for half of the input AC wave, it is called as half wave rectifier. The circuit using two diodes shown in figure 14.19 gives output rectified voltage corresponding to both the positive as well as negative half of the AC cycle. Hence, it is known as full wave rectifier. Here, the P side of the two diodes are connected to the ends of the secondary of the transformer. The N side of the diode are connected together, and the output is taken between this common point of diodes and the midpoint of the secondary of the transformer. So, for a full wave rectifier, the secondary of the transformer is provided with a center tapping, and so it is called center tap transformer. As can be seen from figure 14.19c, the voltage rectified by each diode is only half the total secondary voltage. Each diode rectifies by each diode is only half the total secondary voltage. Each diode rectifies only half of the cycle, but the two do so for alternate cycles. Thus, the output between their common terminals and the center tap of the transformer becomes a full wave rectifier output. Note that there is another circuit of full wave rectifier which does not need a center tap transformer but needs 4 diodes. Suppose the input voltage A with respect to the center tap at any instant is positive. It is clear that at the instant voltage at B being out of the phase will be negative as shown in figure 14.19. So, diode D1 gets forward bias and conducts, while D2 being reverse biased is not conducting. Hence, during this positive half cycle, we get an output current and a output voltage across the load resistor RL as shown in figure 14.19c in the course of the AC cycle. When the voltage at A becomes negative with respect to center tap, the voltage at B would be positive. In this part of the cycle, diode D1 would not conduct, but diode D2 would giving an output current and output voltage across RL during the negative half cycle of the input AC. Thus, we get output voltage during both the positive as well as negative half of the cycle. Obviously, this is a more efficient circuit for getting rectified voltage or current than the half wave rectifier. The rectified voltage is in the form of pulses of the shape of the half sinusoids. Thus, it is underdirectional. It does not have a steady value. To get steady DC output from the pulsating voltage, normally a capacitor is connected across the output terminals parallel to the load RL. One can also use an inductor in series with RL for the same purposes. Since these additional circuits appear to filter out the AC ripple and give a pure DC voltage, so they are called filters. Now we shall discuss the role of capacitor in filtering. When the voltage across the capacitor is rising, it gets charged. If there is no external load, it remains charged to the peak voltage of the rectified output. When there is a load, it gets discharged through the load load and the voltage across it begins to fall. In the next half cycle of rectified output, it again gets charged to peak value. Figure 14.20. The rate of fall of the voltage across the capacitor depends inversely upon the product of capacitance C and the effective resistance RL used in the circuit and is called the time constant. To make the time constant large, value of C should be large. So capacitor input filters use large capacitors. The output voltage obtained by using capacitor input filter is nearer to the peak voltage of the rectified voltage. This type of filter is mostly widely used in power supplies. 14.8 Special Purpose Pn Junction Diodes. In this session, we shall discuss some devices which are basically junction diodes but are developed for different applications. 14.8.1 Xenon Diode. It is a special purpose semiconductor diode named after its inventor Xenon. It is designed to operate under reverse bias in the breakdown region and used as a voltage regulator. The symbol for Xenon diode is shown in figure 14.21a. Xenon diode is fabricated by heavily doping both P and N side of the junction. Due to this, depletion region formed is very thin, is less than 10 to the power minus 6 meter, and the electric field of the junction is extremely high. It is 5 into 10 to the power 6 voltmeter even for a small reverse bias voltage of about 5 volts. The IV characteristics of a Xenon diode is shown in figure 14.21b. It is seen that when the applied reverse bias voltage V reaches the breakdown voltage Vz of the Xenon diode, there is a large change in the current. Note that after the breakdown voltage Vz, a large change in the current can be produced by almost insignificant change in the reverse bias voltage. In other words, Xenon voltage remains constant even through current through Xenon diode varies over a wide range. This property of Xenon diode is used for regulating supply voltages so that they are constant. Let us understand how reverse current suddenly increases, and at the breakdown voltage we know that reverse current is due to the flow of electrons, minority carriers from P to N and holes from N to P as the reverse bias voltage is increased. The electric field at the junction becomes significant when the reverse bias voltage V is equal to Vz. Then the electric field strengthens is high enough to pull valence electrons from the host atoms on the P side, which are accelerated to N side. These electrons account for high current observed at the breakdown. The emission of electrons from the host atoms due to high electric field is known as internal field emission or field ionization. The electric field required for field ionization is of the order of 10 to the power 6 volt per meter. Xenon diode as a voltage regulator. We know that when the AC input voltage of rectifier fluctuates, its rectified output as fluctuates. To get a constant DC voltage from the DC unregulated output of a rectifier, we use a Xenon diode. The current diagram of a voltage regulator using a Xenon diode is shown in figure 14.22. The unregulated DC voltage filtered output of a rectifier is connected to the Xenon diode through a series resistance Rs such that the Xenon diode is reverse biased. If the input voltage increases, the current through Rs and Xenon diode also increases. This increases the voltage drop across Rs without any change in the voltage across the Xenon diode. This is because in the breakdown region, Xenon voltage remains constant even though the current through the Xenon diode changes. Similarly, if the input voltage decreases, the current through RS and Xenon diode also decreases. The voltage drop across RS decreases without any change in the voltage across the Xenon diode. Thus, any decrease in the input voltage result in decrease of the voltage drop across RS without any change in voltage across the Xenon diode. Thus, the Xenon diode acts as a voltage regulator. We have to select the Xenon diode according to the required output voltage and accordingly the series resistance RS. 14.8.2 Optoelectronic Junction Devices. We have seen so far how a semiconductor diode behaves under applied electrical inputs. In this section, we learn about semiconductor diodes in which carriers are generated by photons. Photon excitation. All these devices are carried optoelectronic devices. We shall study the functioning of the following optoelectronic devices. First, photodiodes used for detecting optional signal. Photodetectors. Second, light emitting diodes LED which converts electrical energy into light. Third, photovoltaic devices which convert optical radiation into electricity. Solar cells. First, photodiode. A photodiode is again a special purpose Pn junction diode fabricated with a transparent window to allow light to fall on the diode. It is operated under reverse bias. When the photodiode is illuminated with light, photons with energy HV greater than the energy gap EG of the semiconductor, then electron hole space are generated due to the absorption of photons. The diode is fabricated such that the generation of EH space takes place in or near the depletion region of the diode. Due to the electric field of the junction, electrons and holes are separated before they recombine. The direction of the electric field is such that electrons reach N side and holes reach P side. Electrons are collected on N side and holes are collected on P side, giving rise to an EMF. When an external loads are connected, current flows. The magnitude of the photocurrent depends on the intensity of incident light. Photocurrent is proportional to incident light intensity. It is easier to observe the change in the current with change in the light intensity. If a reverse bias is applied, the photodiode can be used as a photodetector to detect optical signals. The circuit diagram used for the measurement of IV characteristics of a photodiode is shown in figure 14.23a and a typical 1 to 5 characteristics in figure 14.23b. Second, light emitting diode. It is a heavily doped Pn junction which is under forward bias emits spontaneous radiation. The diode is encapsulated with a transparent cover so that emitted light can come out. When the diode is forward biased, electrons are sent from N to P, where they are minority carriers, and holes are sent from P to N, where they are minority carriers. At the junction boundary, the concentration of minority carriers increases compared to the equilibrium concentration, that is, when there is no bias. Thus, at the junction boundary on either side of the junction, excess minority carriers are there which recombine with majority carriers near the junction. On the recombination, the energy is released in the form of photons. Photons with energy equal to or slightly less than the band gap are emitted. When the forward current of the diode is small, the intensity of light emitted is small. As the forward current increases, intensity of light increases and reaches a maximum. Further increased in the forward current result in decrease of light intensity. LEDs are based such that the light emitting efficiency is maximum. The fourth, fifth and 1 characters of a LED is similar to that of a SI junction diode, but the threshold voltages are much higher and slightly different diode. For each color. The reverse breakdown voltage of LEDs are very low, typically around 5 volts. So care should be taken that high reverse voltage do not appear across them. LEDs that can emit red, yellow, orange, green and blue light are commercially available. The semiconductor used for fabrication of visible LEDs must at least have a band gap of 18 eV. Spectral range of visible light is from about 0.4 μm to 0.7 μm, that is from about 3 eV to 1.8 eV. The compound semiconductor gallium arsenide phosphide GaAs 1-XPX is used for making LEDs of different colors. GaAs 0.6 P 0.4 e.g. 19. eV is used for red LED. GaAs e.g. is equivalent to 1.4 eV is used for making infrared LED. These LEDs find extensive use in remote controls, burglar alarm systems, optical communications, etc. Extensive research is being done for developing white LEDs which can replace incandescent lamps. LEDs have the following advantage over conventional incandescent low lamps. First, low lamps operational voltage and less power. Second, fast action and no warm-up time required. Third, the bandwidth of emitted light is 100 angstrom to 500 angstrom, or in the other words, it is nearly but not exactly monochromatic. Fourth, long life and ruggedness. Fifth, fast on switching capability. Third, solar cells. A solar cell is basically a Pn junction which generates EMF when solar radiation falls on the Pn junction. It works on the same principle, photovoltaic effect, as the photodiode, except that no external bias is applied and the junction area is cut much larger for solar radiation to be incident because we are interested in more power. A simple Pn junction solar cell is shown in figure 14.24. A PSI wafer of about 300 μm is taken over which a thin layer equivalent to 0.03 μm of NSI is grown on one side by diffusion process. The other side of PSI is coated with a metal black contact on the top of an SI layer. Metal finger electrode or metallic grid is deposited. This acts as a friend contact. The metallic grid occupies only a very small fraction of the cell area, is less than 15%, so that the light can be incident on the cell from the top. The generation of EMF by a solar cell when light falls on it is due to the following three basic processes: generation, separation and collection. First, generation of EH space due to light, with HV is greater than EG close to the junction. Second, separation of electrons and holes due to electric field of the depletion region. Electrons are swept to N side and holes to P side. Third, the electrons reaching the N side are collected by the front contact and holes reaching P sides are collected by the back contact. Thus, P side becomes positive and N side becomes negative, giving rise to photovoltage. When an external load is connected as shown in the figure 14.25a, a photocurrent IL flows through the load. A typical IV characteristics of a solar cell is shown in figure 14.25b. Note that the 1 to 5 characteristics of the solar cell is drawn in the fourth quadrant of the coordinate axis. This is because a solar cell does not draw current but supplies the same to the load. Semiconductors with band gap close to 1.5 eV are ideal materials for solar cell fabrication. Solar cells are made with semiconductors like Si. Eg is equal to 1.1 eV GaAs. Eg is equal to 1.43 eV CdTe. Eg is equal to 1.45 eV CuInSe2. Eg is equal to 1.04 eV, etc. The important criteria for the selection of a material for solar cell fabrications are: first, band gap equivalence to 1.0 to 1.8 eV. Second, high potential absorption equivalence to 0.10 to the power 4 centimeter to the power of -1. Third, electrical conductivity. Fourth, availability of the raw materials. And fifth, cost. Note that the sunlight is not always required for a solar cell. Any light with photon energies greater than the band gap will do. Solar cells are used to power electronic devices in satellites and space vehicles, and also as power supply to some calculators. Production of low-cost photovoltaic cells for large-scale solar energy is a topic of research. 14.9 Digital electronics and logic gates. In electronic circuits like amplifiers, oscillators introduced to you in earlier sessions, the signal current or voltage has been in the form of continuous time varying voltage or current. Such signals are called continuous or analog signals. A typical analog signals is shown in figure 14.27a. Figure 14.27b shows a pulse waveform in which only discrete values of voltages are possible. It is convenient to use binary numbers to represent such signals. A binary number has only two digits, 0 say 0 volts and 1 say 5 volts. In digital electronics, we use only these two levels of voltage as shown in figure 14.27b. Such signals are called digital signals. In digital circuits, only two values represented by 0 or 1 of the input and output voltage are permissible. The section is intended to provide the first step in our understanding of digital electronics. We shall restrict our study to some basic building blocks of digital electronics called logic gates, which processes the digital signals in a specific manner. Logic gates are used in calculators, digital watches, computer robots, industrial control systems, and in telecommunications. A light switch in your house can be used as a sample of a digital circuit. The light is either on or off depending on the switch position. When the light is on, the output value is 1. When the light is off, the output value is 0. The inputs are the position of the light switch. The switch is placed either in the on or off position to achieve the light. 14.9.1 Logic gates. A gate is a digital circuit that follows certain logical relationship between the input and output voltages. Therefore, they are generally known as logic gates because they control the flow of information. The 5 common logic gates used are NOT, AND, OR, NAND, NOR. Each logic gate is indicated by a symbol and its function is defined by a truth table that shows as the possible input logic level combinations with their respective output logic levels. Truth tables helps understanding the behavior of logic gates. These logic gates can be released using semiconductor devices. First, NOT gate. This is the most basic gate with one input and one output. It produces one output if the input is 0 and vice versa. That is, it produces an inverted version of the input at its output. This is why it is also known as an inverter. The community use symbol together with the truth table for this gate is given in figure 14.28. Second, OR gate. An OR gate has 2 or more inputs with one output. The logic symbols on the truth table are shown in figure 14.29. The output Y is the 1 when either input or in A or input B or both as 1 seconds. That is, if any of the input is high, the output is high. Apart from carrying out the above mathematical logic operation, this gate can be used for modifying the pulse wave form as explained in the following examples. Third, AND gate. An AND gate has 2 or more inputs and one output. The output Y of the AND gate is 1 only when input A and output B are both 1. The logic symbols on the truth table for this gate are given in figure 14.31. Fourth, NAND gate. This is an AND gate followed by a NOT gate. If inputs A and B are both 1, the output Y is not 1. The gate gets its name from this NOT and AND behavior. Figure 14.33 shows the symbol and truth table of NAND gate. NAND gates are also called universal gates since by using these gates you can release other basic gates like OR, AND and NOT. Exercises 14.12 and 14.13. Fifth, NOR gate. It has 2 or more inputs and output. A NOT operation applied after OR gate gives a NOT OR gate or simply NOR gate. Its output Y is 1 only when both inputs A and B are 0. That is, neither one or input or the other is 1. The symbol and truth table for NOR gate is given in figure 14.35. NOR gates are considered as universal gates because you can obtain all gates like AND or NOT by using only NOR gates. Exercise 14.14 and 14.15.
Thank you for being till the end. I hope this has helped you. If so, give thumbs up, like, share, comment, save, download and subscribe. You can support us by following in other platforms. That link is in the description. Well, thank you. See you later. Maybe never.